Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. Welcome to my AP Physics exam preparation video series. Over the next several weeks, I will be releasing a sample free response question for each of the 4 AP Physics exams so that students can familiarize themselves with what kinds of questions will be asked and how the AP exam will ask them to demonstrate their knowledge. As a tutor working with students all over the country, I know that not every student has the opportunity to work with released materials prior to exam day, and this series is intended primarily to help those students. AP Central lists the following types and number of free response questions students can expect to see on the AP Physics 1 exam. There will be 1 question on experimental design, 1 on qualitative-quantitative translation, 1 paragraph length response or paragraph argument, and 2 short answer questions. The question in this video is type number 1, experimental design. We'll take a look at AP Physics 1 2019 free response question number 3, which dealt with conservation of mechanical energy. Although as a lab-based question, you can also work in projectile motion, though I'm going to focus on the energy aspects. A projectile launcher consists of a spring with an attached plate as shown in figure 1. When the spring is compressed, the plate can be held in place by a pin at any of 3 positions, A, B, or C. For example, figure 2 shows a steel sphere placed against the plate, which is held in place by a pin at position C. The sphere is launched upon release of the pin. A student hypothesizes that the spring constant of the spring inside the launcher has the same value for different compression distances. Part A, the student plans to test the hypothesis by launching the sphere using the launcher. Part 1, state a basic physics principle or law the student could use in designing an experiment to test the hypothesis. Again, I'm going to focus on conservation of mechanical energy, and we have 2 ways that we can approach this. We can do elastic potential to kinetic energy, or we can do elastic potential to gravitational potential. And it will be easier since parts 1 and 2 were scored as a whole. We'll talk about scoring after we talk about part 2. Part 2, using the principle or law stated in part A1, determine an expression for the spring constant in terms of quantities that can be obtained from measurements made with equipment usually found in a school physics laboratory. Well, like I said, we can use conservation of energy in 2 ways. We could have elastic potential energy is equal to kinetic energy, and we'll work that one through first. Elastic potential energy is, of course, 1/2 kx squared, which will be equal to 1/2 mv squared. And when we solve this for k, we will get mv squared divided by x squared. If we decided to focus on elastic potential energy to gravitational potential energy, we could orient the launcher upward, and we'll get to that within a couple slides. We'll have 1/2 kx squared equals mgh. And so when we solve for k, we will have 2 mgh divided by x squared. So here is our scoring. We're going to have +1 for an equation that is consistent with the law or principle written in part A1. We are going to have a point for, and I lost it. There we go. Every video, I lose it at some point. Lose my cursor. Super fun. Lost it at like, how? This is so hard. But I only have so many colors, guys. I only have so many colors. Okay, so let's try this again. we are going to get a point for a valid equation that contains measurable quantities and includes the spring constant. And then our third point is going to, and I'll put it underneath the pair, is going to be for a correct and valid algebraic expression spring constant and the expression must be solved for K. Part B, design an experimental procedure to test the hypothesis in which the student uses the launcher to launch the sphere. Assume equipment usually found in a physics laboratory is available. In the table below, list the quantities and associated symbols that would be measured in your experiment. Also list the equipment that will be used to measure each quantity. You do not need to fill every row. If you need additional rows, you may add them to the space just below the table. So I've color-coded this a little bit. You'll notice I used dark blue for the things involving kinetic energy, and I used lighter blue for the things involving potential energy. And so we're going to have some quantities we're going to have to measure regardless of which way we're going to do this, which way we're going to do this lab. We're going to need to measure the mass of the sphere. We'll use the symbol M, and we'll measure it with the triple beam balance or digital scale. We are going to need to measure the spring compression distance X. We can use a ruler or a meter stick for that. And now if we want to focus on gravitational potential energy, we are going to need the maximum launch height of the sphere, h, and we could use a meter stick or video analysis to get that. And if we want to focus on kinetic energy, we're going to need the launch velocity of the sphere when it emerges from the launcher, symbol V, and we can use a motion sensor for that. And the measurements and equipment and procedure were all scored together, so I won't handle any scoring until we've talked about the actual procedural steps. So part B continued. Describe the overall procedure to be used to test the hypothesis that the spring constant of the spring inside the launcher has the same value for different compression distances referring to the table. Provide enough detail so that another student could replicate the experiment, including any steps necessary to reduce experimental uncertainty. As needed, use the symbols defined in the table and/or include a simple diagram of the setup. So again, we've got two ways we can do this with kinetic energy versus potential, so I'll go through it with you twice. So we're going to measure the mass of the sphere with the balance. We can aim the launcher vertically. Compress the spring to position A and measure its compression with a ruler. Launch the sphere and measure the maximum height the sphere reaches above the release position with a ruler or meter stick. Repeat for 3 trials total at position A, then repeat this whole procedure with the pin compressed to positions B and C. So, now that we have a procedure, I am actually going to pop back to the measurements tab, so I've got a little bit more room to write. So we're going to get a point for listing relevant or appropriate equipment. I'm just going to fill in here because I have room. So relevant or appropriate equipment that matches all measured quantities in the experimental procedure. And there is a note that this point could be earned even if the sphere is not actually launched. So apparently, when these were actually scored, some students must have decided to try to test this without actually launching the sphere. And, so there are places where they could still earn some points. So here in our procedure, we need to describe measurements of quantities sufficient to determine the spring constant. So that's going to match up back with our equations, right? So we're going to get a point for I should say of quantities, measurements of quantities. Apparently I'm just having some difficulty like writing clearly at the moment. Oh my goodness, let's just fix that so that it's just more legible. There we go. We are going to need, we're going to get a point. I'm going to put this one up at the top just to have a little more space. We're going to get a point for a plausible procedure. In other words, can be done in a typical physics lab. Involves launching the sphere to determine the spring constant. We are going to get a point for launching the sphere from at least two different positions. We're going to get a point for attempting to reduce uncertainty, for example, with multiple trials at a pin setting. And it is noted that this point can also be earned if the sphere is not launched. So now let's talk about what our procedure could look like for Kinetic energy, we can measure the mass of the sphere with the balance. Aim the launcher horizontally on a level surface toward a motion sensor. Compress the spring to position A and measure its compression with a ruler. Launch the mass and get the launch speed from the motion sensor. Repeat the process for 3 trials total at A, then repeat the whole procedure with the pin compressed to positions B and C. And we don't need to score this again because we've already been over the scoring once. In part C, describe how the experimental data could be analyzed to confirm or disconfirm the hypothesis that the spring constant of the spring inside the launcher has the same value for different compression distances. So again, we had 2 different procedures. So we're going to have 2 different ways to handle the analysis. And I really like to do things graphically, not just based on calculating with equations. So I'm going to discuss with you how you could analyze this data graphically as well. So we'll start with gravitational potential energy. You can take the average of the maximum heights for each position, calculate the spring constant for each position using a half kx squared equals mgh, which we saw before gave us k equals 2 mgh divided by x squared. Compare the k values for the 3 positions. If they agree within experimental uncertainty, or if they're close within a few percent, or if they are about the same, then the hypothesis is confirmed. So let's talk scoring here. We're going to get a point for comparing the measurements of the spring constant or a suitable proxy at all 3 possible compression distances. Which of course were A, B, and C. Let me fix that, make it more legible. Okay. And our second point is for considering uncertainties, experimental uncertainties, in confirming the hypothesis. And let me write that and then I'll explain. So for example, language that the scoring guidelines gave included if numbers match with it, let's try that again. If the numbers match within experimental uncertainty, like I wrote up above, or if the numbers are about the same. So those are just examples of language, and I incorporated them both into my example. And it's important to note that they actually had a note in the scoring guidelines. This point is not earned for saying if the numbers are the same or similar phrasing that does not address the experimental uncertainty. So you shouldn't expect in your lab work necessarily to get exactly the same value every time. They should be close, but they're probably not going to be perfect. Hence the emphasis on if the values agree with an experimental uncertainty, if they're close within a few percent, if they are about the same, but not if they are the same. So again, I like plotting data to get some trends and patterns. And to do that, for this one, you could take the average of the maximum heights for each position. The equation mgh equals a half kx squared suggests that we could plot h versus x squared to see if there's a linear best fit with an r value close to 1. If the data has a linear fit, its slope will be equal to k divided by 2mg, so k equals 2mg times the slope. If there's not a linear fit with an r value close to 1, then the hypothesis is disconfirmed. So this was not offered up as an alternate solution in the scoring guidelines, but I am offering it as a way that I like to analyze data. So let's talk about part C. If we're going to do kinetic energy, we could take the average of the launch velocities for each position, calculate the spring constant for each position using a half kx squared equals a half mv squared, which we saw earlier, k equals mv squared divided by x squared. Compare the k values for the 3 positions. If they agree with an experimental uncertainty, are close within a few percent, are about the same, then the hypothesis is confirmed. We're going to plot this one, then take the average of the launch velocities for each position. The equation 1/2 mv squared equals 1/2 kx squared suggests to plot v squared versus x squared to see if there's a linear best fit with an r value close to 1. If the data has a linear fit, its slope will be equal to k divided by m, so k equals m times the slope. If there's not a linear fit with an r value close to 1, then the hypothesis is disconfirmed. Part D. Another student uses the launcher to consecutively launch several spheres that have the same diameter but different masses, one after another. Each sphere is launched from position A. Consider each sphere's launch speed, which is the speed of the sphere at the instant it loses contact with the plate. On the axes below, sketch a graph of launch speed as a function of sphere mass. So let's talk about what this should look like. So we are going to have the same elastic potential energy each time because we're always using position A. And we're looking at speed versus mass, so that's going to suggest kinetic energy 1/2 mv squared. So let's do some algebra here. The halves are going to go away. And if I rearrange to solve for v squared, I'm going to get v squared equals kx squared, which is the constant, times 1 over the mass. So we're generally going to have some kind of inverse relationship where as the mass gets bigger, the launch speed actually decreases. And it was really important to talk about the equation behind that because that helps explain why this isn't just linear downward. So for our points, for our scoring, we're going to get a point for a curve where the launch speed always decreases with increasing sphere mass. And then our second point is going to come for a curve that is entirely concave up and has the launch speed always increasing, etc. Sorry, always decreasing with increasing mass. Oh my goodness. So this allows you, if you messed up and drew it as a linear relationship, you could still get 1 out of 2 points for the curve where the launch speed always decreases with increasing sphere mass, but you do have to have considered that inverse kind of relationship in order to get the second point. So I hope you have found this solution to an AP Physics 1 experimental design question helpful. If you have a video solution request for my YouTube channel, you can send it to physicsproblemrequests@gmail.com, though I won't be putting up any of them until my AP Physics video series is concluded. If you need some assistance, you can send your problem and the work you've done on it so far to freephysicshelpline@gmail.com. There's a limit of 10 questions per academic year. If you'd like to learn more about my online physics tutoring services, you can email me at brandyheflinphysics@gmail.com. You can visit my website, virtualphysicsofficehours.com, and you can find me on Facebook. I'm Physics Tutor Brandy. So just a few notes. AP is a registered trademark of the College Board. The College Board does not endorse or recognize this video or my services. All of the materials presented are available on AP Central at the link shown here for the AP Physics 1 exam, and those materials include the release free response questions, the scoring guidelines, and sample student responses and commentary. I strongly encourage students to review those sample responses to get a feel for the different levels and quality of the responses prepared by the students who took these released exams live, and to see what the scorers for that year were looking for and how they decided to award points. If you have questions, you can email me at brandyheflinphysics@gmail.com. I'm Physics Tutor Brandy. I love physics, and I love helping you. Until next time.